Let's look at a design example where we want to design an active bandpass filter using the circuit that we've analyzed previously, and I've copied that down here below. And we want this bandpass filter to pass frequencies between 250 Hz and 3 kHz. And in that pass band, we want the gain to be 10. And we're told also to use R of 20 k ohms. And so as we've talked about before, we could of course adjust the ratio between these resistors here or these resistors here in order to have some additional gain. For simplicity, they've all just been left as an R value, and sort of as a way to sort of have training wheels on this problem, we're just given this R value of 20 k ohms. Of course, we could arbitrarily choose this value, and then we'd want to make sure that our currents, our voltages, everything is operating within specification. But again, here we've just sort of made it a little simpler by being given that value. So sort of three pieces of information we need to solve for are two corner frequencies, omega 1 and omega 2, and that information is going to be related to here, and we're going to get that by adjusting values of our two capacitors C1 and C2. Our gain we're going to get by adjusting values of our RI and RF in our gain stage at our inverting amplifier. So let's take a look at each one of those three items. So let's first consider from our low pass filter, which is going to be setting omega 2. So from our low pass, we're going to set omega 2 with C1. And so remember, in general, our omega is equal to 2 pi times our frequency, and because these frequencies are given in hertz, we need to relate that back to the equations that we had in terms of omegas. So we know that that omega is equal to 1 over R times C1 for this particular low pass circuit that we're considering here. So now we can solve this for our C. So we know our C, and so let me come down here to a new line to get plenty of space. So we know our C1 is then going to equal 1 divided by R 2 pi F2. And so our omega 2 is the upper frequency, so that's going to be our 3 kHz. So we have our R value, which we're told to use 20 k, so I'm going to go ahead and write that out as 20,000 ohms, our 2 pi, and then our omega 2 is 3 kHz. Again, I'm just going to go ahead and write it out, take everything back to sort of the base units, and then just a 1 in the numerator. So that gives us a value of approximately 2.653 times 10 to the minus 9th farads. So what we can say then is our C1 is going to be approximately 2.653 nanofarads. So we're going to do a similar thing with our high pass filter. So our high pass filter, we're going to set our omega 1 with C2. And so again, coming back up here to our high pass filter, we can see this piece in the middle is our high pass filter. So by adjusting that C2, we can set our omega 1 value. So we have omega 1 is equal to, in general, 2 pi f. And we know from previous analysis that that corner frequency is equal to 1 over R C2. So again, what we're going to do is we're going to rearrange that to solve for C2. So we have C2 is equal to 1 divided by R 2 pi times F1, plugging in values. We have the 20k for R, 2 pi, and then our F1 was 250 Hertz. And 1 in the numerator, and so that's going to give us approximately 3.183 times 10 to the minus 8 farads. And so what that's going to be is C2 is approximately 31.83 nanofarads. And so these are two sort of typical values of capacitors. A 1 farad capacitor, remember, is a very large capacitor. More often in electronics, at least, we're going to see capacitances in the nanofarad or the microfarad range. Okay, so we've addressed sort of two of the issues. We've got our frequencies omega 1 and omega 2 set, and of course those correspond to these two F values of 250 hertz and 3 kHz. And now what we want to do is address this gain of 10. So from our previous analysis, we had an equation for the passband, for the gain in the passband. So passband gain was given by K is equal to RF divided by RI times omega sub 2 over omega 1 plus omega 2. And so of course we can just rearrange that and say that this ratio of RF divided by RI is equal to K times omega 1 plus omega 2 divided by omega 2. And plugging in values, we know we want this gain to be 10. And then for our omegas, we didn't calculate them explicitly, but of course we can just put in our frequency in hertz, 250 for omega 1 plus 3000 for omega 2, and then multiply by 2 pi. And then in the denominator, we have our 3000 hertz times 2 pi. And what we see is that our 2 pi is going to cancel out. So really we have this same equation. We could have substituted these omegas for F's and we would have had the same result. Okay, so plugging that in, we get that this ratio of RF over RI is approximately equal to 10.83. So what we can do now is we can arbitrarily choose values of one resistor. So I'm just going to arbitrarily say, let's let Ri equals 10 k ohms. And what that means then is that our RF needs to be 10.83 times that. So we can say our RF would need to be approximately 108.3 k ohms. And so what we would want to do, either with calculations or simulations, is then go back and make sure that these resistance values and these capacitance values provide sort of what we want happening, but also we want to check, for instance, our current levels to make sure all of the power for our devices are within their operating ranges so that we're not damaging anything.